before I continue, I want to make sure this is, yes, okay, cool, we are recording. So find all values of x in the interval from 1 to 4 at which f has a critical point. Classify each as the location of a relative minimum, a relative maximum, or neither. Justify your answers. Okay, so for this problem, now what I think you kind of should recognize here is what are they asking for in this question? They want to know when f has a critical point. F is going to have a critical point when f prime is equal to 0. But what I want you to notice is what happens when I set f prime equal to 0. So 0 equals 7x minus 19. Oh man, this is nasty. So what you should see here is that now AP is not going to trick you. They're not going to give you kind of this big nasty thing and expect you to be able to solve this. What they want you to do here is they want you to graph this. And they want you to figure out where are the zeros. So you're going to graph, and then you're going to find your zeros. So now they want you to know when is it going to be a relative min, a relative max, or neither. And so what you kind of are looking at here, and you can look at, oh, I see your hand, Alexis. Go ahead, Alexis.
Okay, just really quickly, I was wondering if points of inflection also count as critical points or no?
So points of inflection, a critical point is a max min or any time that the derivative is 0, the first derivative. When the first derivative is 0, that should be when the, no. It's not always going to be points of inflection are not necessarily critical points. They can be, but not always. And so just to kind of clarify, so they can be, but oftentimes if they are, it's because of something like a cusp where it wouldn't have a derivative. But yeah. So a POI would be for the second derivative equaling 0, so I wouldn't classify it as a critical point. Does that clarify?
Thank you.
Yeah.
Yeah, thank you so much.
Cool. So now relative min, relative max, or neither. So you're going to want to know, when is f prime less than 0? Less than 0. Sorry, that's not what I mean. I mean, when is it negative to positive? I was going to try to save it and go from less than 0 to greater than 0. And then we want to know when f prime goes from positive to negative, because that's going to tell you whether it's a max or a min. I see you, yeah, Abby. The other case is going to be, sorry, I think you recognized, I thought I made a mistake, but I don't think I did, because I think I was right the first time. Is that what you were going to tell me, Abby? No?
No.
Go ahead. Go ahead.
So I just had a question about like decimals, I guess.
Mm-hmm.
So I found one of the zeros for the function,
yeah,
1.999992. So would it be fine if we just said that was 2, or are they looking for us to?
Yes. Now, okay. So
yeah. Abby, I didn't get that same 0. Maybe I plugged mine in wrong, but did you?
So let's graph it. Let's see what we get. Okay. Desmos. Okay. So we have 7x squared. X. Where are we? Function. No, squared. There we are. 7x squared.
Well, that's probably why, because I didn't put in 7x squared.
Me neither.
Oh, wait. And because it's not 7x. squared. It's 7x. Sorry, Abby. Ugh.
Oh,
Guys,
yeah.
this distance learning is making me crazy. I am so sorry. Okay, so 7x minus 19 multiplied by, then you have your sine function, x squared. That's where the x squared is. X squared, whoa, minus 4x. Still, whoa, plus 4. Woo! Okay, now we can see why they're restricting our interval. Look at this craziness here. Oi. Okay, so come down to 1, 4. Now, this is the derivative. So we want to know, when is this going to be 0? So now you can, and on your graphing calculator, you can look for intersections here. On Desmos, you can see them pretty clearly because they actually point them on the graph. So this would be 2, 0, so that's one critical point. And then look what they do here. They actually do something that's kind of nice. They round this to the 3rd decimal point, which is exactly what you would do on the AP test. If you wanted to keep it as that big long decimal, you could, but I think 2.714 is perfectly fine. Now, are we done? Do we have all of our critical points yet? There's one more. There's a 3rd one. Right here.
Wait, do we need to account for endpoints, or is that only when we're dealing with integrals?
Good question. What do you think? Read that question. Do you think this is going to be is this going to require endpoints? There's a specific word here. You guys want to help out?
If it says like critical points or relative min, relative max, that's different than absolute min and absolute max.
Yes. Okay. So, Amon, if it said absolute min, absolute max, 100%, you would include those endpoints. But you are also correct in thinking that this is going to be something where, oh, wouldn't this likely be more of a situation for integrals? Yes, that doesn't necessarily mean it won't show up, but it is something that's more in the integral world because it's on a closed interval, so you're looking at areas. So to answer your question, Amon, we are looking at just the mins max within the interval, not the endpoints. So, and then if we go back to Desmos, so you can kind of see what's happening at 2. Is that going to be a max or a min? And so this is why having a graphing calculator is so important, because there's nothing changing at 2. It stays negative. And so that would be quote unquote neither. Now then, excuse me, you want to see, is it going from negative to positive or positive to negative? To answer your question, Abby, about decimals, if it was the case of like 1.999999, I believe if you rounded it to 2, because of the way that the AP uses rounding, you technically would be correct, or they would have taken 1.999. Yeah, so both of those should have worked. Okay, so Julio. All right, now, again, I'm not gonna do all the problems, but I will definitely get you guys started. Now, for this one, for part B, it says use the line tangent to the graph at x of 1.5 to approximate f of 1.8. So in order to figure this out, we need a couple things. So we have y minus y1 equals m times x minus x1. And so you can kind of make this easy on yourself and then just set up what is m, what is y1, what is x1, and then just fill in the equation. Now, the part that we want to remember, though, is that are we done after we put these all into the equation? What do you guys think? No, we're not, because it asked us to also find that approximation. So this is the tangent line approximation. I haven't seen a lot of secant line approximations, but secant line approximations are more average value of the function when you're given, you would do kind of the average value using like the graph or a table. Okay, so here we know what y1 and x1 are because it says x1 is 1.5 and then y1 was given to us. Said it is 3. And then so m is going to be what? So what do you guys think? What do you guys think is going to be m? How do we find that?
If you plug in 1.5 into your derivative, you should find the slope of the tangent.
You got it. F prime 1.5. Here we are. Okay. And then so once you get these pieces, you plug it in here, and then you're going to have y minus y1 m x, or whoops, that wasn't the x I wanted, because what I want to do here is I'm actually going to plug in that 1.8 minus that x1. And that's how you're going to get your approximate value. Now, remember, the approximate value that they want is they want this. What is that y value? Okay. So on the interval from 1.5 less than or equal to x less than or equal to 1.8, f prime of x is less than 0 and f double prime of x is greater than 0. So is the approximation found in part B an overestimate or an underestimate? Okay, so hold on. So I just want to know, because I don't want to give you the solution, but I think I can give you a hint here. Oh, we don't need to really know what value we got in part B in order to answer part C, just to clarify. Okay, so what we need to know here is what is the interpretation of what does this part mean and what does this part mean? So if f prime of x is less than 0, what does that mean in terms of the function? So I'm not going to give you the full solution here, but what I am going to show you, I'm going to put a table down here. So this table is going to save you if you have it as like a cheat sheet on your available to you while you're taking the test. So if f is concave up, then that meant the first derivative was increasing and the second derivative was positive. If the first function is concave down, that means we can also do this the other way. So instead of saying this, if I say my second derivative is negative, that meant that that first derivative was decreasing, and therefore the function as a whole was concave down. Now, the other thing you want to write in this little table is what happens when that first derivative is positive? Well, our function itself is increasing. And what happens when our first derivative is negative? The function itself is decreasing. So we have to think about what type of function do we have based off of what's been told to us. So because our first derivative is negative, okay, so we're here, that means we're decreasing. And it says that f double prime of x is positive. We're here. Oops. So that means we're concave up. So we're concave up, but we're decreasing. So you have to think about the fact that that means we look something like this. So I'll put an exaggerated one over here. Concave up, decreasing. Much better. Okay, Cool. So now that last piece, part D, it says, using the mean value theorem, explain why the average rate of change of f over the interval cannot equal 6.5. Okay, so I want to give you guys an opportunity to kind of work through this. What do you guys think would be your first step here? So using the mean value theorem, you have to explain why the average rate of change of f over the interval can't equal 6.5. So there's a couple of things you know, and you do need to include the mean value theorem. So what do you guys think? What do you have to start with? How would we start this part?
Do you have to
Find.
Oh,
go ahead? Sorry.
was that you, Andrew?
Sorry.
Yeah, go for it. What do you think?
But yeah, you would find you find the average rate of change over f over that interval.
I don't know if I didn't get a lot of that. Let's hear from Alexis. You may have said the same exact thing. You were kind of breaking up a little. Alexis, why don't you tell me what you were thinking you were going to do?
Okay, I think the first thing you have to do is state that it's continuous and differentiable.
Yes, yes, absolutely. So, in order to do that, how do you know that's true? What key piece of information? That. So, you need to say, since, whoops. F is a twice differentiable function, therefore continuous. Whoops. Then, so what do we have to do next? So I think, oh, Aman, were you going to say something?
Yeah. When I saw this, I remembered that example that you gave us, and you used something called like proof by contradiction or something.
Mm-hmm.
Is that
Yeah.
What it is?
Yes. So essentially what we want to do here is, so we're going to basically calculate, can we get 6.5? So in order to do that, what we need to know is, okay, so there are a few things. We can either prove that f of 4 minus f of 1 all over 4 minus 1. So basically, we have to say that this doesn't exist, or there is no such, whoops, maybe I'll put this as a different letter. There's no such C value that's going to give us the derivative of 6.5. So this can be something where you can really let your graphing calculator do some heavy lifting, because again, you are allowed to use your graphing calculator here. So what do you think I should perhaps graph? I'm going to graph 6.5. So go back to Desmos, and if I go to, I believe it is y equals 6.5. Okay. So if we look at this graph, oops, there we go. So that blue line up here doesn't even touch our function between that interval. So this could be one of the explanations that you give for the reasons as to why. So you could say in graphing the derivative, which is pretty much, that's kind of the only way you do this, unless you want to use integrals, which like you could, but it's not going to be on your AP test. So why would you bring them into your AP test unless you're more comfortable with that? They wouldn't dock you points for using a concept of calculus that they're not quote unquote testing on, because you get points for your justification, not a justification in a specific way necessarily. So what I would say is that, 6.5 doesn't intersect this function between the interval of 1 and 4. So I know that that means there's no possible value where those two are going to be equivalent. Therefore, there's no such C value, which is the one I chose for f prime of C. Okay, cool. So how are we doing on this one? So just as a reminder, because this is kind of like your final, I'm not going to go over full answers because I do want to give you a chance to really like go all the way, but I'm going to do big chunks. Okay.
So would it be okay to say that in graphing the derivative, f prime of C does not intersect 6.5 in the interval, over the interval from 1 to 4?
So I would probably say you need a little bit more. And so therefore we can conclude that there is no value that would give us f prime of x equal to 6.5. So you want to say like, so how do I phrase it? I think it's more of, you don't want the grader to have to go the extra mile to be like, oh, okay, so that's what they mean, right? You want to say like, because 6.5, the line y equals 6.5 does not intersect the graph f prime of x over the interval from 1 to 4, there exists no such x value that can give us f prime of x equal to 6.5. Yeah, go ahead, Alexis.
Is it okay that you did it that way because they ask you to use the mean value theorem? So like, does just graphing it and seeing if it intersects like count as using the mean value theorem?
Let's look at yes. So and here's why. Okay, because I'm looking at the justification that they have written here. And so because what you can claim, and this is just because so here's what you have to think about. For the mean value theorem, the very general idea is the average rate of change is equal to the instantaneous rate of change. But if there is no instantaneous rate of change equal to the one you're looking for, then there's no way that the mean value theorem could be applied necessarily. So by trying to show whether or not there's a derivative equal to that value, you are applying the mean value theorem. Does that make sense? So by saying, essentially by saying that there's no such derivative giving us this value, we can say like the mean value theorem, by the mean value theorem, if there's no such instantaneous rate of change giving us 6.5, there will be no average rate of change giving us 6.5. Yeah. And so we can conclude that because it's kind of, if there's an average rate of change equal to 6.5 by the mean value theorem, there has to be an instantaneous rate of change equal to 6.5. But the opposite of that is also true. So if there's no instantaneous rate of change equal to the value, then there's no average rate of change equal to that value. Yeah.
So could you also do it like the first way you kind of showed, just like proving that the average rate of change is not 6.5?
Yes, if you did do it that way, Alexis, you would have to use an integral, but because you get a graphing calculator, you can use your graphing calculator to calculate that integral for you, because you can just take the integral of f prime. Yeah. And so that would be exactly what I would do. I would actually, that might be a pain in the butt. Okay. If I'm thinking in terms of this year's AP test, you could, because here's what you would need to do first. You would need to anti-differentiate the f prime of x. So you would need to get the antiderivative and then plug in 4. So it would be a little bit more work because you would have to take the integral. Whoops, sorry. Okay. You'd have to take the integral of this whole thing. And so this is kind of a nasty thing to have to integrate. But like, because you're allowed to use the internet, you can go into you can't do active browsing, but there are tools that you can like download that are anti-differentiation calculators, which, I mean, that's totally something that you are allowed to do on the AP test this year, but it is gonna, just be a little extra time if you're not familiar with the technology. But yeah, so Alexis, you could do that, little bit longer process. Okay, let's go to how much, okay. I'm actually, let me go through, because there is a related rates question on this practice AP test. So, is it this second one? I believe. Let me go back through, because I had a whole list of all of my things and what they're all testing. Okay. So, okay. So this is, I think, would this one be better? Okay, let's do question 3, because that's, I think, a little bit more unique. Okay. So, question 3. All right. So, oh, whoopsies. Andrew left and came back. All right. Sorry, Andrew. Don't worry, we didn't do anything super major. Okay. So for question 3, we're going to talk about, so it's during a chemical reaction. So this one is a question, and the reason why I picked this one is because this is, it's very closely aligned with the AP test. And it was a question that was flagged by College Board as a good one to review. Now, just so you guys know, all of your AP questions on your mock AP test, they cover at least 3 units. So, number 5, during a chemical reaction, the function y equals f of t models the amount of the substance present in grams at time t seconds. At the start of the reaction, t equals 0, there are 10 grams of the substance present. The function y equals f of t satisfies the differential equation dy dt equals negative 0.02 y squared. Now, so use the line tangent to the graph y equals f of t at t equals 0 to approximate the substance remaining at time t equals 2 seconds. So in order to use the tangent line, we need to remind ourselves, okay, so we need a slope, we need a y1, and we need an x1. Okay, now our x1 in this case is a t, just so we kind of make that connection there. Okay, so we're looking at, okay, well, when t is equal to 0, that's what we're looking at. So let's see if we have an initial point. So when t is equal to 0, let's go back. Oh, hey, we have an answer for our y1. So when t is equal to 0, y is equal to 10 grams. Now, we have to figure out what is the slope. So what we actually are looking at here is, and this is, I remember why I put this question on here. So we need to know what is the slope at t equals 0. Okay, so for part A, you do not want to do this. I saw this so many times. So I'm going to do the wrong thing, and I want you guys to tell me, why was it the wrong thing to do? Okay. All right. Go for it, Iman.
You forgot to separate the variables, or you put the y's with the y's, and then
we're not there yet. We're not there yet.
Okay. Never mind.
You're like a step ahead of us. You're going into the next step.
You plugged in the wrong variable.
I plugged in the wrong variable. Now, in this problem, I don't know if I would expect to see the mistake that happened on one of your other free response questions that is here, because it's a t equals 0. But there was another case where your initial condition was not a 0 something. It was like a 10 something or a 5 something. So always make sure you understand what is the correct value here. This is supposed to be that y value. So we need to make sure this is a y value. So this is negative. So now we can erase this. Hold on. This is what I want to do. 0. And we're going to say, we plugged in the wrong variable. Okay. So, wrong. Now, make sure you figure out what is the slope when t equals 0. So that's going to be negative 0.02. And we're going to plug in 10 squared here. Okay. So, whoops. Ooh, my notability. Okay. So, part B. Now, using the given differential equation, you have to determine the graph and whether or not the differential equation could be modeled by this graph. So, give a reason for your answer. Now, this is a good question because these are one of those questions where it's really hard to figure this answer out online. So, using the given differential equation, determine whether the graph of f could resemble the following graph. So, this is our function, whoops, here we are. So y is equal to f of t, t equals 0, there are 10 grams. Now, so let's look at what's happening with the slope or the derivative. So our derivative, we have a negative constant. But it's a negative multiplied by a square. So the square is kind of going up. And so that does get larger. But do you think this is kind of representative of this graph here? So I want to give you guys a second. I want you guys, you can talk amongst yourselves if you want, or just kind of like pause and think about it yourself. But what do you think? You want to think about this is the equation for our derivative. In other words, this is our slope. This is how our graph is changing, right? And so you want to think about, okay, so if I started at t equals 0 and y was 10, does it make sense that I'm kind of going down like that? So I'll give you guys a minute to think about that. You can also, if you want to, feel free to talk about it.
Usually when I see y squared graphs, I think of the like sideways parabola.
Mm-hmm.
So, and that's not really what is being shown, but
Yeah.
I don't know.
And I was thinking too that because if the derivative is always going to be negative, then that means that f, or like what came before, is going to be decreasing at all times. And so this one's decreasing, but it starts going up. So I'm like, I'm suspicious.
Yeah. Anyone else?
Also, also, the derivative is y squared. Shouldn't the original function be like x cubed function?
I see what you're saying. I do want to touch on what you just said, Andrew, and also kind of relate it to what Melina said. When you guys are talking about, so Melina, you were kind of talking about how a y squared graph normally kind of looks like a sideways parabola. Think about this more of like this y squared, y represents the function. So this could be like any value. This could be an a here. Okay. And so don't think about the y in terms of like an actual y value and how that's going to look, because the y represents the function, not necessarily all those y values in the xy plane. Yeah. And so, Andrew, in terms of the cubic, I could see how that might look a little bit kind of cubic, but I think out of what you guys were discussing, I think overall the biggest part that was said was what Aman was saying about how because our derivative here is negative, it's always decreasing, or the other way you can think about this, it's never increasing. Never. What's happening here? It's increasing. That never happens in this. And so that's another way that you could justify that. So you would say that the derivative has a negative value, therefore the derivative will always be non-increasing or will always be decreasing. And so there is a case where there is a shift or a change from decrease to increase in the graph shown. Therefore, I know this is not a good representation of it. Okay, now part C. Okay, so part C, this is what we were talking about earlier with the finding the expression for y equals f of t by solving the differential equation dy equals dt equals negative 0.02 y squared with the initial condition f of 0 equals 10. So for this problem, this is exactly what your mind was thinking before, Aman, with we have to do the separate and integrate. So this one, and this is what I want you guys to think of when you do this. The word that comes to my brain is always cross multiply, but it's not really cross multiplying. But you want to move your basically this has to get moved over to the other side. Whatever's on the bottom has to get moved over to the other side. That's just, first off, that's one of the ways that this has to work. And then, so from there are a couple of ways that this might pan out depending on the problem. So let's say that I actually know what my y function is. If I know what my y function is, then I could just plug that in here, but that would be that's not super likely. So what you do have to do here is you actually are going to factor out that y squared. Now you can do this in one of two ways. You can either divide out that y squared, or you can divide out that negative 0.02 y squared. It does not matter. Both will get you the same thing, but usually the constant kind of tags to the other value and y squared goes to the other side. So you have dy over y squared equals negative 0.02 dt. And then, so from here, you're going to separate, integrate, and when you integrate, you put that c on the right. So this is going to be 1 over y, I believe, is what we get. Wait, negative 1 over y. Yeah. And then negative 0.02. Oh, that negative's going to cancel itself out. So, yeah. Now, I am going to do something. It is a little slick. I am going to make these both positive. And yes, I am keeping this as a plus C. Okay. So, and can I do that? Yes, I can. Because you want to think about this as before you add that constant on there, you think of what are my integral pieces? Can I factor out any constants? And you can factor out that negative there. So, and then from here, you're just going to plug that in and solve for y. So solve for c, solve for y. Okay. And solve for y. Okay. Now,
So,
oh, go ahead.
is it possible when you have 1 over y, like, I don't know, like my brain just thinks if you flip the y to the top, you can just flip everything else on the x, I'm at the t side to the bottom.
Yes. Yes, you can. Melina, I feel like you're reading my mind right now because I was looking at that. I'm like looking at my work and I'm like, oh, I hope they make this connection. Yes. I want to kind of just really touch briefly on what you were talking about. Okay. So basically, since we have 1 over y equal to, now what I would recommend doing first, Melina, solve for c in this format, then solve for y by flipping. So once you get that c value, we have, I mean, is it really going to make that big of a difference, Melina? Not so much. It's just going to make your life a little bit easier with the solving. But what I want everyone to make the connection is, since we can flip this, this also gets flipped. So we end up with y equals 1 over, like that. Yeah. And I mean, again, I would solve for c before doing that flip. It's just going to be easier. Okay, cool. And then for part D, it says, whoops, determine whether the amount of the substance is changing at an increasing or decreasing rate. So in order to figure this problem out, we need to know, what does it mean to be increasing or decreasing at an increasing or decreasing rate? So basically, they want to know the rate of change. So the rate of change, that's y prime. But is y prime changing at an increasing or decreasing rate? So they basically want to know, what is y double prime, I believe, is what we want to look for here. So now, in order to figure this piece out, you want to figure out, okay, what is y double prime? So let's say we'll just, let's throw out a case. Let's say y prime is positive, or it's negative. Y prime is negative. We already know that, right? And instead of y prime, I'm going to do the same notation. Okay. So dy dt. So this is the notation for the second derivative. And then, so dy dt is negative. So we know that it is decreasing because it is negative. We need to know, is this positive or negative? Sorry. Yes. That is positive and negative. I thought I did it backwards. But if it's positive, it's going to be decreasing at an increasing rate. So if you think about that, that means it is, so perhaps we started from 100 and then we went from 100 to 80 and then we went from 80 to 40. That's decreasing at an increasing rate. Versus decreasing at a decreasing rate would be something like, maybe we started at 100 and we went from 100 to 80 and then we went from 80 to 70. So that's decreasing at a decreasing rate. And so it's the rate of change is getting smaller between each individual value versus getting larger between each individual value. And that's going to have to do with the second derivative. All right, cool. So I'm actually going to pause here because I think, did I have that fourth question? Now, this fourth question, this is something, let me look over all parts of this fourth question because I just want to clarify this does have a lot of parts. All of the parts in this question can be seen on your AP test this year. So, yes, go ahead, Alexis.
I have a question about the last one.
Yeah, absolutely.
So would that be a type of problem where you find the acceleration and velocity and see if the signs match, or would you just find the acceleration?
For this one?
For part D.
Yeah, so for part D, this one, you technically, because of the way that the question was set up, you only need to find acceleration because we know what technically velocity is. Now, keep in mind, Alexis, this is not a position equation, but we know what the velocity is, and our velocity is always negative.
So
Yeah.
you're not like seeing if the acceleration and velocity have the same sign and then deciding like from there. Like it's not one of the like speeding up or slowing down
It
ones.
is not. You are correct.
Okay.
Yeah.
And is that because of the way it's worded?
Well, this is because it's more of it's not a position question. It's more related to the rate of certain amounts of things. And so when you're talking about the rates of change of amounts of things, you want to know not what is the relationship between its position and where it's going, but rather what is the relationship between the quantity that I have and whether it's going up or down. Does that clarify kind of, because the question, so Alexis, because this question is talking about a chemical reaction and not in a substance, and we're talking about grams in a substance and talking about over a particular time with a particular model, this doesn't set itself up for a position function. If it said, instead of during a chemical reaction, if it said the position equation for the function y equals f of t models a certain thing, then that would lead us to velocity acceleration. But it's because it doesn't say anything about a position of a particle.
Okay.
Yeah. Okay. So yeah. Okay. So for question 4, we have, and to clarify, this covers parts that you will want for your AP test. So for question 4, the graph of the function f consisting of 3 line segments and a quarter of a circle is shown above. Let g be the function defined by g of x equals from 1 to x of f of t dt. So we have to find the average rate of change of g from x equals -5 to x equals 5. And so in order to find the average rate of change here, so what are we going to have to do for our average rate of change? Do we need g? Do we need g prime? G double prime? What do you guys think?
G of 5 minus G of -5 over 5 minus -5.
Okay, now this right here, this area accumulator is something that we did in unit 10. And so 10-2, and this is something that I've kind of been going back and forth between. So part A, where is it? Part A is we're defining we're applying properties of definite integrals. That's what we're doing. And so because of the fact that this is now going to be a definite integral that we're calculating, that's why we have this. The area accumulator, the way that we were doing it, we were applying the area accumulator more for initial value and initial position problems. So it was, and it's because the way that it's set up is that that's really how you use those integrals in the AP test. So for this, you are going to need to figure out, okay, so if I'm starting at 1, so the integral, this is going to be the integral from 1 to 5 of f of f, or sorry, f of t dt minus the integral from 1 to negative 5 f of t dt. So they kind of snuck in a little property here. If you remember, what's going to happen here? Something weird happens here.
You switch the sign and then you look you switch 1 with negative 5.
Absolutely, yes. And so this is because of the order of the limits, or sorry, the order of your bounds. You want them going left to right because of the way that the direction is going and you're accumulating that distance. Otherwise, it's a negative area you've accumulated. So let's go ahead and make that change. I'm going to make this a positive and change these to a negative 5 and a positive 1. Cool. So then all you have to do here is, okay, so I have 1, 2, 3, 4, 5. Okay, so what is this area here, here to here? And then I'm adding it to this area here.
Quick question.
Yeah.
When they give you a graph like this with like pretty definite shapes in it, is it easy to assume that they want you to do this kind of area accumulator problem?
Yes.
Okay.
Yeah. And that's a great statement that you made, Abby, is like they're giving you a graph that has recognizable shapes. This is not a situation, this is not our other graph. This is not this graph. I mean, we know kind of what these shapes are, but if we had to find the area here, that would take us so long, lots of tears, lots of sad days. So they would definitely give you something. If it was an area accumulator, you need more recognizable shapes, because I know how to find the area of a triangle, a quarter circle, and a trapezoid.
I have a question.
Yeah, go ahead.
So I know that we flipped the sign because we had to go from negative 5 to 1, but these are also all negative because they're under the x-axis. So, like,
that is another great catch. Because these are under the x-axis, they are going to be negative. And so it is a negative area. And now what you kind of can think about is that the negative area actually, that's part of the way that you could have, no, I'm not going to go there. So this will be a negative value. Now, just so you guys know, that's not always going to be the case. It's just happens to be how this is set up. This could have very well been like this. So this could have very well been, I'm going to draw it, in a different color. So this could have been the same thing like this. And then it could have gone up like this. And then it could have gone over like this. And you could have had this would be a positive amount and this would be a negative amount. So it still could have, it's just the way that the graph worked that it just so happens that from negative 5 to 1, it is all negative. But yes.
So does that mean that once we apply the negative from flipping it, that they'll all become positive?
No. So when you flip it to make it from negative, so, okay, there's 2 flips you have to think about. So when we're talking about from 1 to negative 5 of f of t dt, okay. So when we're talking about this integral, we're starting at this 1 and we're going to the left. So we're going in a negative direction. So this is already going to equal a negative something. Do you get that? Because we're going in the left direction. So that's something that comes from the fact that our interval, or these limits of integration, are reversed. So that's what this negative comes from. And then we also had the negative from the minus that made this a positive, but we haven't included anything about the negative value of our areas. So the area still will be negative, even though we applied a negative because we had to flip the limits of integration. That didn't change the fact that this is now all positive. Yeah? Okay, cool. So I'll leave that there. So part B, it says find the instantaneous rate of change of g with respect to x at x equals 3, or state that it does not exist. So we need to know the instantaneous rate of change, which in other words is the derivative or the slope of the tangent line, dy dx, f prime. You can say it however many ways you can. So basically, when it says find the instantaneous rate of change of g with respect to x at x equals 3, or state that it does not exist, it wants to know what's g prime at 3. That's what we want. Okay, and then so for part C, it says on what open intervals, if any, is the graph of g concave up? So justify your answer. Now, one thing I will tell you for part C, though, it does say, on open intervals, on what open intervals, if any, it still is referring to the world of -5 to 5. So don't think like, oh, -10 to -8, it's concave up. No, they don't care about that. It's still within that world. They're just giving you the possibility that there might not be any in this particular interval, but that's not the case. So what derivative, or what derivative am I looking for the concavity here? First, second,
Second derivative.
second derivative. And I'm looking for when it's concave up, so I'm looking for when the second derivative is what?
Positive.
Positive. Okay. So now in order to do this, you can look at your graph. So if g is equal to the integral of f, so I'm doing this very basic, that means g prime is equal to f, and so that means g double prime is equal to f prime. Okay, so where am I looking? So, oh, sorry, I didn't even put my f prime there. So I'm looking for essentially when is g double prime positive, or when is f prime positive. So what is perhaps another way that you might say that?
When is f increasing?
Nice. Way to go. So you can also think of it as when does f have a positive slope? That's another way too. Great. So if we're looking at this, this is going down, this is 0. We're looking for strictly when it's concave up. So we want to know when is it increasing. Now, it doesn't matter if it's below or above the x-axis. What matters is the angle that it's going up or angle that it's going down, depending on concavity. So that means, let's pick a fun color. We'll do pink. Here it's increasing, and here it's increasing. Keep in mind, it is going to be a closed interval because it has those endpoints here and here. But again, College Board won't really care so much about your brackets. And so what you have to do here is in part C, part C, so it says on what open interval, so that actually does tell you don't want to have the equal sign. Is it concave up? Justify your answer. You need to know g prime of f of x when it is increasing. And so you have to kind of consider, oh, it says, this is interesting. Because when f of x equals 0, what is that? When f of x equals 0, those would be critical points. Nope. Yes. Oh. Sorry. I'm looking at the wrong section. Now we have it. Okay. So you have to say the graph is concave up, and the reason why can be these two reasons why. Okay, so part D, which was the one I was just looking at, it asked us to find all x values where g has a critical point. So g is going to have a critical point when g prime is equal to 0, or when f is equal to 0. And then you have to classify each as a max or a min. So you're going to have to look at, okay, so when is f of x equal to 0? Well, it's going to be 0. Whoops, let's get a different color. Let's get orange. So we have this one right here and this one right here. So we have those 2 points. All right. And you're going to consider, are they a max? Are they a min? How do you know? And I think you just have, what do you guys think? So max, min, neither. I think I spelled neither wrong. Okay, so I'm gonna give you guys actually a second. So it's these 2 points right here, those 2 orange dots. And what do you guys think those are gonna be? Are those gonna be maxes, mins, neither? What do you think?
So it's usually if it goes from, oh wait, if it goes from positive, or this one, the one that's at 1 at x equals 1 goes from negative to positive, so that should be a minimum.
Minimum, you are correct. What about the other one? What's happening there?
It's neither.
Neither, nothing's happening. It stays under the x-axis, so it doesn't change negative to positive or positive to negative. It goes negative to negative. So this is neither. Okay, cool. And Melina, I really liked your justification of it went from negative to positive, therefore it is a minimum. That is perfect justification. Okay, cool. So I do want to go over some related rates questions for you guys. Let's go through. I wanted to look at, okay. So there were a couple of questions. I know I posted a bunch on the FRQ, the FRQs that I gave you guys. I'm wondering if, I'm gonna set this up. Did I give you this one? Because this is a good one to do. I did give you this one. So maybe I'll do this one. Okay. But before I go into this, are there any particular problems you guys want to go over from the list of free response questions? It's totally okay if you don't. Okay, so I do want to, and okay, let's go to, let's do, oh, that's a good one. Okay, I'm gonna also put this one in. Okay. Oops, almost there. Okay, so I'm going to do the 2019 number 6 question. And so I believe that is currently in my drive. 2019, excuse me, number 6. So I'm gonna do this one with you guys. And then, yes, I'm also going to do one more. That's a good one. That's a tricky, is it? No, it's only so tricky. Okay, so, and then I'll put this one in. We'll do this one next. Okay, this one's gonna take a second because I have to upload it right now. I was a little behind this morning, but that'll be okay. It'll be okay. Okay, so let's start with this one, and let's see. All right. Was there one that I just, 1996, okay. No, is it not here? Name. Okay, I'll find it. It'll come back. Oh, it's because I'm in the wrong section. That could be helpful. All right, so here we are. Thank you for your patience. Okay. Lovely. Okay, so let's go to, boom, boom, boom. Oh my goodness, where did you go? All right, I am having technical difficulties. Give me a moment. It might need to be. I just give it a second to load. Okay. There we are. Okay, cool. So let's get started. Now, for this one, so these are, and I highly, highly recommend if you haven't done so already, really want you to be understanding the related rates problems and using differential equations. Differential equations and solving differential equations, finding a particular solution of a differential equation, those are all things that I would expect them to want you to know. So for this first one, we have, consider the curve defined by 2x squared plus 3y squared minus 4xy equals 36. So we have to show that this differential equation dy dx is indeed equal to 2y minus 2x divided by 3y minus 2x. So what we have to do here is we just have to take this derivative. So pretty straightforward. You're going to start with your derivative. And the key that you're going to want to remember here is that what happens when you take the derivative of y. When you take that derivative of y, you're going to need to have a dy dx in there, because otherwise, now you can also write that as y prime, totally perfect personal preference, but the key that's really going to come into play here is when you have the minus 4xy, because you're going to need to do a, that's going to be 4 times y plus 4x dy dx. You got to do a little product rule here, and that's going to be equal to 0. Now, you can go ahead if you want to keep that as -4 and just distribute that negative. Otherwise, what you do once you get to this point, you want to isolate these pieces. So you have 4x, 4y. I move those over to the other side. So I have 4y minus 4x. And that's equal to, I'm going to pull out dy dx. I have 6y minus 4x. And then, as you can see, this is going to work out super nicely. And dy dx. Now, keep in mind, 4y minus 4x over 6y minus 4x. This is an equivalent solution, but because you're matching, go the full way. dy over dx. 2y minus 2x over 3y minus 2x. And that's it. You don't have to do more. You really just need to see, did I calculate this correctly? Can I get the same derivative? And the answer is yes, you can if you use the appropriate derivative rules. So now for part B, you're actually going to be applying the information you have in the context of the problem, because you have to find the slope of the line tangent to the curve at each point where x is equal to 6. So you have to find the slope when this is equal, or sorry, find the slope of the line tangent to the curve at each point on the curve where x equals 6. So what you have to do here is you're going to be plugging in, I believe the last time I did this, we plugged 6 in. Let me double check. Okay, yes, you do this. Okay, so you plug 6 into, so look what they did here. They plug 6 into the solution to calculate what is the y value you have, and then you're going to calculate the derivative at those two y values. So let's do that. Okay, so we have find the slope of the line tangent to the curve. So first step we're going to do is x equals 6. So we have 2x squared minus, 2x squared, did I do this right? Plus 3y squared minus 4xy equals 36. So you're going to go ahead and plug in that 6 value here. And you're going to solve for your y's. Okay, so what you end up getting here, so you have 2 times 36, so that's 72. 3y squared minus 24y. Okay, so you have negative 36, 3y squared minus 24y. Okay, so you're going to go ahead and make yourself a nice little 3y squared minus 24y plus 36 equals 0. So then factor out a 3 here. You get, whoa, sorry. My niece wanted to FaceTime. Hold on one second. Okay, I have to rejoin. All right, so okay, so here we are. Back to it. So you're going to factor out the 3. You get y squared minus 8y plus 12 equals 0. I think you guys kind of can get the picture here. And so you're going to plug in. So you have y equals 2, y equals 6. But you're not done when you get down here, because again, they want to know what is the slope of the line tangent to the curve. So you're going to calculate what is dy dx at, so you have 2 y values when x is 6. So you have to calculate dy dx at 2, 6 and 6, 6. Okay, so for part C, find all positive values of x, or find the positive value of x at which the curve has a vertical tangent line. Show the work that leads to your answer. Okay, So for this
Wait,
question,
I actually have a question about where we just were.
yes, go ahead.
When we were solving, when we plugged in x equals 6,
Yeah.
We were left with y values,
Yes.
or we should have solved for y values. So wouldn't the points be 6, 2, and 6, 6? Or, because you wrote 2, 6.
Yes. Thank you. You are correct.
Okay, okay.
Yes. Thank you. Good catch. Good catch. All right. Yes. You are correct there. Thank you. Okay. So moving to part C, find the positive value of x at which the curve has a vertical tangent line. So you want to look for, what does this piece mean? It has a vertical tangent line. What does that mean? What does that mean in terms of slope? What do you guys think?
It's undefined.
It is undefined, yeah. So this has an undefined slope. Now, an undefined slope would mean, for this case, because you have, and I think this was something that is also included in the, when you see these words, think of doing this. So when you have a vertical tangent line or an undefined slope, what you have to do here is you actually have to have your derivative. So you want, I'm giving you a general example here. So you want f prime of x put into some type of fraction. So let's say a over b, and you set that equal to an undefined slope. Basically what you're saying is that this denominator here, b, is equal to 0. So that's what you're looking for here. So when is my denominator 0? Whoops, when is the denominator 0? Okay, so in order to do this, you know dy over dx is equal to 2y minus 2x over 3y minus 2x. So you have 3y minus 2x equals 0. And so you're going to solve what is the positive x value for which the curve has a vertical tangent line. And you just solve for that x value here. Okay, let's do, whoops. Okay. So
After you do this next problem, also go over from 2015 number 4.
2016 1-6.
2017 problem number 4.
Okay. Yeah, that's a good one to go over. I can do that one too. Yeah. But so just so you know, Andrew and everyone else, I'm happy to do that. I'll probably end up going a little over time, which I have no problem with. But if you can't make the time, that's totally okay. All right.
Yeah,
So,
that's okay.
oh no, I'm totally yeah, I'm happy to go over it. Don't worry, Andrew. Let's do that one before. Oh, go ahead.
My question is, when we're doing this, do we have any values that we plug in to 3y minus 2x, or?
You're just solving for, so, or wait. Find the positive value of x at which the curve has a vertical tangent line. So yeah, I believe this should be 3y minus 2x equals 0. And 2y, yeah. So, I forgot a step here. Thank you, Melina. Keeping me honest. Okay, so we do need to kind of go, let's do this. Okay. So 3y equals 2x. So we get y is equal to 2/3 x. Thank you. We need a little bit more. From here, you need to find the positive value of x. And so in order to do that, you need to go back to the original equation. And so from here, you plug in 2/3 x squared plus 3y squared minus 4 2/3 x y equals 36. Okay, so, and then from here, what are we doing from here? Because if it's a vertical tangent line, then, wait a second, hold on.
Well, we know that,
And-
it's a vertical tangent. We already know that by plugging in y equals 2/3 x takes care of that.
Yes, and if you see my work, I plugged in x to x, so that may have definitely been confusing. So 2x squared, thank you. There we go. That looks more like it. Okay, and now you're gonna solve for your x value. I was like, why? All right. Okay, cool. So, and then from here you solve for your x value. So solve for x. And now I remember this. You should get a square here, but it only wants the positive value. So make sure you only include the positive value. Okay, cool. Part D. All right, so let x and y be functions of t that are related by the equation 2x squared plus 3y squared minus 4xy equals 36 at time t equals 1. And the value of x is 2, and the value of y is -2, and the value of dy dt is 4. Find the value of dx dt at time t equals 1. Okay, this is a good problem because, and I've seen this happen a few times before. So if you've done any type of unit conversion, if you remember unit conversion from chemistry, then you can kind of understand what I'm going to do here. So see how I want dy dt, okay? I want to know what is the rate of change of my function with respect to time. I want to know dy dt if I have these pieces, right? So in order to do this, I have dx here, and they cancel when I multiply these two pieces together. So x and y are functions of time t that are related by that equation. So when t equals 1, the value of x is 2, the value of y is -2, and the value of dy dt is 4. So we need to know what is this value equal to at time t equals 1. Okay, so let's do it. Okay, so we need to know what is dy dx. Well, we know what dy dx is because we have the equation for it. So we know what is dy dx, but we need to know specifically at time t equals 1, so we need to know when x is 2 and y is -2. So we need to know what is dy dx when x is 2 and y is -2. So that is, you have 2y minus 2x, 3y minus 2x. And so you have, this is equal to -4 minus 4 over, that's going to be -4 minus 4, -12, sorry. Nope, -6, guys. -6. I am sorry. -6 here, because that is, yep, 3 times -2, so that is -6. Okay, so you get -8/10 here, or -8 over -10, or 4/5. So you know that dx dy, or sorry, dy dx is 4/5, so that's what you have here, 4/5. And you know, well, dy dt is equal to 4. So you have dy dt, which is 4. And so it becomes super easy. Then it's just multiply 5 on both sides. And then divide by 4. So you end up with dx dt is 20 divided by 4, which is 5. Sorry, my sister's texting me. Anyways. Okay. So that's finishing part D. Just so you guys know, we are a little limited on time. I am happy to go into the next problem, but this is not one that you have on the free response question. So I'm happy to go over it if you guys want to see it. I think it's a good one to talk about related rates. And it's one I haven't really seen before. I haven't seen a similar one to it. So if you want to stay and do this problem, just so you know, there's about 8 minutes to 12. Otherwise, I'll probably finish this problem up. And then if you guys have any questions, I'm happy to answer. We also have office hours next Monday.
I think I'm going to get going, but thank you so much for doing the related rate problem.
Yeah, absolutely. Make sure there's also a ton of the practice on the FRQ list, but yeah, and then this will also be, I'm still recording, so this will still be up.
Okay, thank you.
Right, cool.
I have
Bye.
to get going too. I wanted to say thank you.
Yeah, absolutely. Bye, Mon.
Bye. Take care, everyone.
Bye. Okay. So if anyone else is leaving, totally feel free. Okay. Let's talk about.
Yeah, sorry, I have to go too.
Totally. No
Bye.
problem. That's okay. Okay. So for part 6, it says in the figure above, line L is tangent to the graph of y equals 1 over x squared at point P with the coordinates w and 1 over w squared, where w is greater than 0. So point Q has the coordinates w0. Line L crosses the x-axis at point R with coordinates k0. Find the value of k when w equals 3. Okay, so this is kind of one of those problems where you're given a model and you're given certain situations and you have to use the information for the different situations to get your particular answers. So if we have to find the value of k when w equals 3, well, the first thing that I'm probably going to be doing here, I'm going to be plugging in what is w. So when I have w, that's going to be my coordinate 3, and then that's 1/9, 3 over 1/9. That's what I have. Okay, so now when I'm looking at this, it says, okay, so the line, oh, okay. So here's point R. And the coordinates for point R are k0. All right. So we have to figure out what is the value for, I think I know how we're going to do this. So we have to figure out what is the value of k. So we need to know the slope, essentially. We have to find that, we have to calculate the slope in order to calculate k. So, all right. So at point P, line is tangent to the graph of, and point Q, okay, so point Q is W, so that's 3, 0. And then we have this right here, 3, 1/9. Okay. All right. So, Actually, I'm trying to think. What are you guys thinking? What are you guys thinking? I feel like I'm supposed to go Pythagorean theorem here. Let's take a look. Oh, go ahead.
I was thinking that too, but maybe you can use the slope of the tangent line to find the value of k.
Mm-hmm. So that's what I was
Maybe.
thinking too. But see, that we need to know what's the value of the slope, which we don't. Actually though, do we? We could calculate that.
Yeah.
Yeah, absolutely. Okay,
Yeah, because it's a straight line, so the slope is the same.
let's try it, you know? Okay, so if this is a straight line, so here's what I'm thinking. So, and you guys can pause me if I'm wrong. So what I'm thinking, this is my approach. It might be the wrong one. We can take a peek in a second. But what I think we should do here is we're going to take the derivative of y equals 1 over x squared. We're going to take that derivative, and we're going to plug in 3 for that x value and calculate what that is.
Yeah.
Yeah. Okay, so
Yeah.
let's try that. So then if we calculate this, so I'm going to rewrite this as y equals x to the negative second. And so y is equal to, y prime is negative 2 x to the negative third. Okay, cool. So then that means my slope here is, so negative 2 over 3 cubed. So that's negative 2 27ths. Okay. So I think what my next process is going to be is we're going to do 1/9 minus 0 over 3 minus k equals negative 2 over 27. All right.
Yeah.
So let's see if we're on the right track. I want to know if we're on the right track. Okay. Guys, we're doing great. Beautiful. Okay. So you guys can go ahead. That's just algebra. We can move on to part B.
Yeah.
So when W is greater than 0, we have to find K in terms of W. Okay. So anytime we have a positive W value, yeah, so if that's the slope, so yes, because it's a straight line, so we can take that as our slope.
I think we can just do what we did before, except just use letters. Just use variables.
That's kind of what I'm thinking as well, because, so it says for all W that are greater than 0, we have to find K in terms of W. So if we think about this, because we have, so we would basically do 1 over W squared minus 0, over W minus K equals, and I think it would still be negative 27 over 2, or negative 2 over 27.
Yeah.
Yeah, because because as Andrew said and pointed out, it is a straight line. So from here, this is going to be some algebra. So I'm actually just going to cross multiply this. So this is going to be 27 over W squared equals negative 2 W minus K. And then keep in mind, the last piece that we need to do here is we have to have K in terms of W. So 27 over W squared. This is minus 2W plus 2K. So I'm going to add that 2W over here. And then ultimately, last step is we have to divide out that 2. So 27 divided by 2, W plus W equals K. And I think if you leave it like, or sorry, this should be W squared. If you leave it like this, that's,
yeah.
Let's double check what that solution looks like. Let's see. This did not turn out the same way. Hmm.
I think it's the same approach, but I think we just made a
Ooh.
computational error.
No.
Oh,
I think I know why.
Yeah.
I think I know why. Because this was the mistake. We didn't want to set it equal to that. And because that's what threw us through a loop. So,
Yeah.
let's redo this part. Okay. So, basically what you had to do is we had the right start. So, okay, I'm really glad we chose to go over this one because this is a very good problem. Like I said, this is something that's very tricky to do on this year's AP test because it's going to be hard for you to find all the information you need and justify it within the 45 minutes. I mean, within the short time frame, it's going to be so difficult for you to cheat. So why bother? But basically what they did here, if you want to see, they did I have it flipped. The rubric is flipped in the other way. So they have 1 over W squared over W minus K. And then so what they get here is that, did I do that right?
Yeah, that's what you had on the left side. It's just that what we did was when we did -2 over 27, the denominator 27 is equal to W cubed, and we were evaluating at equals 3, so we should have left it as W cubed, and that's what it had.
Clever. Thank you.
Yeah.
Yes. Oh, okay. All right. I'm so glad. Okay. So, Cole, Alexis, did that make sense how we get that this is -2 over W cubed?
Yeah.
So Alexis.
Yeah.
Oh, go ahead.
Could you explain again where you got that from?
Cole, does it make sense to you? Do you want to try to explain it?
No, I'm still working
totally
with
okay.
myself.
That's
yeah,
okay.
I can't go in here.
So Alexis, what we were doing here was we had to calculate. So in part A, we calculated when W was equal to 3, and we got -27, or sorry, -2 over 27. Right? You follow me there? So what was our W value? It was 3. 3 cubed is equal to 27. So we're just replacing that 27 with W cubed. Let me actually do this. And the reason why we have to, do it like this is because, as you guys saw, I got stuck. And Andrew cleverly saw, oh, well, 27 is 3 cubed. And we need to write K in terms of W. So why would we have a 27 in there when we could put a W cubed? Great point. So you want to make sure you're using the -2 over W cubed in this case. So yeah, that's a real slick thing that they might put in there. And so if this is the case, then it's a cross multiply. So we cross multiply, we get W cubed multiplied by 1 over W squared, and that's equal to -2 W minus K. And then from here, it's all algebra. You should get...
Wait.
Yeah. You okay?
Wait.
Mm-hmm.
Hold on. Give me a second.
Okay. All right. So let's go through, let's look at this kind of, and so you guys know, this is an old problem. This is an old problem. So, I mean, this is also something you guys can search for online. Okay. So for part A, let's talk about part A. And so we can kind of, if you do have something like this, Andrew, if you are still thinking, that's totally fine. I'm just going to make sure we go through part A so that you guys are comfortable kind of how would we approach this problem if we saw it again. So for part A, it asked us to find the value of K where W was 3. So what you needed to do here was you really needed to understand what pieces did you have, right? Because that's what I always say. They're not going to give you any piece that you're not going to need. So you need to go back to, well, I need to find the value of K when W equals 3. Well, okay, so P, W over W squared, so that's this one right here. And so I need to know that this is going to be 3, 1 over 9. Okay, so that's 1 point. Now, what else do I need to know? I have to find the value of K. Well, K is R. That's right here. So that's K0. And then I also have to figure out, well, what else do I know? Well, I have point Q. That's here. That's 3, 0. Okay, so what I have to do here is now when it's asking me to find the value of K when W equals 3, I'm asked to find a Y coordinate when I have a point, when I basically have 2 points. And I can calculate my slope using the derivative at that point. So I have a derivative, I can calculate my slope at that point, and then I'm going to use the 2 points and plug them into the slope equation to see, okay, what is that unknown? So it's basically using the derivative formula to calculate what is the instantaneous rate of change at 3, and then you're applying your algebra topics to confirm the derivative you got at 3. Okay, so for part B, Andrew, it does look, let's see what we have here. It does look like we should end up with 3/2 W, which would have been what we ended up with here. Because that W cubed and W squared would have left us with a W minus 2W plus 2K. So this would have been 3W equals 2K. So 3W, whoops, 3/2 W should be K.
Oh, yeah.
Yeah.
Okay.
Okay, so for part C,
Yeah, I think I did something wrong with my algebra.
yeah, this one, it's I'm glad this is that we're choosing to go over this. So suppose that W is increasing at a constant rate of 7 units per second when W equals 5. What is the rate of change of K with respect to time? Okay, part C. Part C is definitely going to be related rates. So this is the one that I think we need the Pythagorean on. I'm going to add an extra page here. Okay. Can I bring this one up here?
I think we'll do it for part D more than part C, I think.
Say that one more time.
I think we use the difficulty in separate C, maybe.
Do part
I
D.
don't know.
Yeah.
Yeah, I'm pretty sure.
Well, maybe we can, let's kind of do the setup of part C and we'll get into part D a little bit more, a little bit deeper. Yeah, because I agree with you. I think part C is, suppose W is increasing with a constant rate of 7 units per second when W is equal to 5. Mm-hmm. So, yeah. And then what is the rate of change of K with respect to time? Yeah, so basically, I think you are correct in that, it is something that, like, it's a little bit smoother. but let's kind of, whoops, come on now. Okay. Oh well, we'll go down. All right. So I believe part C should be, so if we look at it, I want to have a graph because we have the, whoops. Okay. Oh my goodness, I am so sorry with this technology, guys. Okay, so I think that we have here, boom. Okay, so, and then we have the line that's tangent coming down here. And then you kind of have that curve. Like that. Okay, so it looks like this one is that K0. Okay. This is Q. This is P, and this is R. P is 1 over, whoops. 1 over W squared. And this is W0. Okay. So basically what part C is asking us, it says W is increasing. So it's giving us a rate of change of W. So it says that W is increasing at a constant rate of 7 units per second. When W is 5, what is the rate of change of K with respect to time? Okay, so let's look at this. So we have this triangle right here. Okay, so now we are looking at when W is equal to 5. Oops. Okay, so when W, oh wait, sorry. When W equals 5, that would be 5 here. Ah, yes, yes. So 5, 0, and it's changing at a constant rate of 7. So that means this one is going to be, K should be 12, 0. Am I doing this right? What do you guys think?
Wait, are we on part D or part C?
I'm on part C.
Well, I did, well, I saw the question was, what is the rate of change of K respect to time? So that's dk dt, and I wrote dk dt equals dw over dt equals dw over dt times dk over dw. And
You're breaking up a bit.
I saw that we can figure that both out.
I think, hold on. I want to make sure I have the triangle right. But,
Oh, sorry.
oh wait, no.
I don't
Part
think
C
my
won't
internet
use the triangle.
that good. Anyways, so the question was asking.
Yeah, because the question is asking.
Yeah.
Yes. The question is asking
Yeah,
about the rate of change of K.
We're trying to find D, and then we can, that's equal.
Oops. Andrew, you're breaking up a little.
Yeah.
But I think, hold on. I hope it's not my computer. Okay, so dk dt, I think it's, is it D? Yes. Yes. Hold on. I'm going to do this a different way. and make this dw. Okay. This is a tricky one. Okay. So dw dt, okay, so this is what we need. We want this one, and we just calculated that the rate of change dw dk, I believe this is 3 halves. That's the rate of change of w with respect to k.
Yeah.
That's 3 halves.
Yeah.
So we have that 3 halves here.
And
Yeah.
then in the problem, it says that we know that dw dt equals 7.
7. Yeah.
Because the rate of, it says w is increasing at the constant rate of 7 units per second.
Yes. So this would be 14/3 would be dk dt. Okay. Did I do that wrong?
Something a little bit different. I got 21/2.
Yes. Wait. How did I mess that up? Oh. Because if I, wait. No, because if I'm dividing by 3 halves, that's multiply. Hold on.
I think you flipped something.
Yes, you are correct. I think it should be 3 halves. Yeah, I think it should be 3 halves.
No, I think you wrote it as, wait.
Yeah. I think I know what you're gonna say. I think this should be 2/3. Because the way that this is written, dw dk, I think the way that they have it written is the following. They have dw dt multiplied by dk dw.
Yeah, equals dk dt. And then you just plug everything in from there. That's how I did.
Yeah, so this would be 7 times 3 halves. Perfect. Okay. Yes, now I'm with you. Okay. So, because the way I had it before with respect to this guy, it's the rate of change of k with respect to w. That's this. The rate of change of w with respect to k is what is the coefficient multiplying k to get w, is another way you can think of that. Okay, now part D has to be the related rate section because we've set everything up to do the related rate. So it better be a related rate section. And I think it is. Okay, so let's go through real quick and we'll just draw out this little triangle. Oops. Okay. Okay, so
yeah.
What? Okay, so now I believe that the triangle is using, I want to make sure they're using the, here we are. Let's go through. Okay. I don't want to keep scrolling back up. Okay, so we have P, Q, and R. Whoops. And R is K0. This is W0. And this P value is going to be W1 over W squared. Okay. So, coolio. All right. Now, when we're looking at this, we have, okay, so A squared plus B squared equals C squared. Then we have A dA dt plus B dB dt equals C dc dt. Okay. You guys with me so far? Okay. So then we have to think about, so I'm going to just, for me, this is how I do it in geometry. So I'm totally just going to let my geometry brain do its thing right now. Okay. So the distance between Q and R is the distance between W and K. So the rate of change between these is going to be the rate of change between W to K. So what is that going to look like in terms of the dy dx? Okay, so actually let's put in those values first. We have, is it when, for part D, it's asking, suppose that W is increasing at a constant rate of 7 units per second. So dw dt, so I'm going to write this, dw dt is increasing at a constant rate of 7 units per second. So when W is equal to 5, what is the rate of change of the area? So we need the rate of change of the area. So you were with me, but was this the right equation to use? No, no, Ms. McNinch. We needed the area equation. I made it's a rookie mistake. I didn't read the full question. Rookie mistake. Okay, so we're getting down to crunch time. Rookie mistakes tend to happen, and then you're like, wait, I thought 7 plus 5 was 11, but it's not. So we all have those days. Anyways, so we are looking at the rate of change of the area. So we actually need to know what is the rate of change of the height, what is the rate of change of the base, which that rate of change of the base, that's that, that rate of change of the base, which is what I think we had calculated. Yeah. So we're going to do the area is equal to 1/2 base times height. Okay. So now in order to do this, okay. So let's figure out how are we going to calculate this base area. So this, or sorry, not base area, base length. So the base is the difference between W and K. So now I'm just setting up my area formula right now. We haven't even taken the derivative, so we don't have the rate of change of our area formula yet. Now, that next piece that I need in here, what is the height? Well, the height is this piece right here, which goes from 0 to 1/W squared. And so this is going to be 1/W squared. Oops. All right. So I am going to rewrite this. So this is going to be, I'm going to go ahead. Oh, there's a clever thing that I can do here to make this all in terms of W. Which, so I'm looking at the solution and they did this kind of slick move here where they did 3/2, sorry, W minus 3/2. But actually, now that I'm thinking about this, wouldn't that give me a negative value? I think my base needs to go the reverse. So I think my base, instead of W minus K, so instead of going from here to here, I need to start here and subtract my original is kind of what I'm thinking instead. So it needs to be K minus W here. All right. And then, so yeah, because otherwise this is going to be a negative value, which doesn't make sense because it's an area. Okay. So W minus W multiplied by 1 over W squared. So we're just going to go ahead and calculate. We get that's 1/2
Oh,
times.
and then
Yeah.
I think
So that's our area formula that we get. But we need to calculate what is the rate of change of our area. So before I keep going, did we all
Are you
get?
sure it doesn't? What happens to that one, the W with the 1/2 there, right?
Sorry. I think that.
So 1 over 4 W.
I think it should be 1 over 4. Yes. Yes, you are correct. Sorry. Thank you.
Okay.
I was looking at the derivative because the derivative should have a square in it.
I got you.
Yeah. Okay. So now I'm just going to bring us down. Do we have some space here? Okay. So if our area equals, thank you, Cole, 1 over 4W, then we have to figure out what is the rate of change of our area with respect to time. So that's going to be, we can rewrite this as, sorry, not 4. 1/4 multiplied by W to the negative first. And then in taking the derivative here, this negative is going to pop down in front. So negative 1/4 W to the negative second now, because that's negative 1 minus 1. But then this is going to be the key. dW dt. Don't forget it. Because then what you have is that rate of change of the area, dA dt, is negative 1/4 W squared multiplied by dW dt. What is that rate of change? Do we know this? Yes. That's that constant rate of 7. So we're going to plug 7 in here. And then we have to figure out what happened. So what is the rate of change? When W equals 5. So all you're going to do here is you're going to plug in, is it when W equals 5? Right? Yes. You're going to plug in W equals 5 and you're going to calculate the rate of change of the area. So you're going to do dA dt. So this is a fun notation a couple of you have seen. And that's going to be negative 1 over 4. So we get negative 7 over 100. So the rate of change of area is decreasing at a rate of negative 0.07 per second. I think is seconds was the time, I believe. Yes. Okay, cool. Nice. Man, that one was kind of a doozy. Thanks for sticking it out with me. But yeah, so for the AP test, if you haven't done so already, make sure you have the updated email address in your portal. You've looked at kind of the AP demo on how to take your AP test and what to do that day. Also, if you are planning on not taking any of your AP tests, do not click the e-ticket. If you click the e-ticket, it marks you off as having taken the test. So don't click the e-ticket until the day of your test. And just as a reminder, I am going to have office hours on Monday. I'm pretty much 10 to 2. I'm just going to be on Zoom. and I'll be here. Come in if you want. And then Tuesday's the math work day, but I mean, I'm going to be available, but I also know you guys are taking your test, so I'm probably not going to help you if I get questions. But anyways, hopefully I see some of you guys Monday. Otherwise, I hope you have a great rest of your week and weekend. Got some
Thank
nice
you.
weather coming in. Hopefully that's
Yeah.
fingers crossed we can enjoy the weather.
Thank
Yes.
Thank
All right.
you.
You're
All right.
welcome. I will
Bye.
see you guys soon and have a wonderful rest of your day. Bye, guys.
Thanks. Bye.